So you may get the feeling that when we're looking at rotational things, angular velocity and angular acceleration and angular position and all of that, we're really just repeating all the math we did when we were looking at linear or translational. That means things that move from place to place. And pretty much you would be right. So we can draw a line between concepts as they appear in the linear variables and in the rotational variables. So for example, position. In rotation, that's the angle. In the translational variables, that's the position vector r, which you know is the x component in the x direction plus the y component in the y direction plus the z component in the z direction. We don't do a vector on top of the angle here just because it's a little hairy mathematically what's going on there, but you don't have to worry about that. But we also have velocity, and we met that in the linear world. Velocity was just the derivative of the position with respect to time. And that's also true in the rotational world. The angular velocity, omega, is equal to the derivative of the position with respect to time. And similarly, acceleration. In the linear world, the acceleration is the derivative of the velocity with respect to time, or the second derivative of position with respect to time. In the rotational world, the angular acceleration is equal to the derivative of the angular velocity with respect to time, and the second derivative of the angular position with respect to time. We do have an inertia term. In the linear world, that was just mass, which we symbolized with an m. In the rotational world, that was the moment of inertia, which we symbolized with an I, and you can get by looking at all the objects, making up something, and multiplying by how far away they are from the axis of rotation squared. So moment of inertia, and both of these guys are the thing that basically say how much acceleration you're going to get for a given force or torque on you. Which brings us to the next thing, which I'll just call the thing that causes acceleration. In linear world, it's force. In angular world, it's torque, which we symbolize with the tau, and the torque is equal to the moment arm crossed with the force that's causing it. And for both of these, we have now the inertia, the thing that causes acceleration and acceleration, so we can get Newton's second law. In linear world, that is the sum of all the forces acting on an object is equal to that object's mass times its acceleration. In rotational world, that is the sum of all the torques acting on an object is equal to its moment of inertia, its mass thing, times its acceleration. So exactly the same kind of math is going to go into these two sorts of problems. You'll find all the torques or all the forces, and you'll set that equal to the inertia thing, mass or moment of inertia, times the acceleration, either A if it's linear acceleration or alpha if it's rotational acceleration. We have kinetic energies for both. So in linear world, it's 1/2 the mass times the velocity squared. In rotational world, it's 1/2 the moment of inertia times the velocity squared. Has to be, of course, the angular velocity when you're rotating. And we have, work. Work is the change in energy here. And if it's due to a force, you can say it is equal to the force dotted with the displacement, Over here, work is also the change in energy, but now you can do it's the torque, dotted with the displacement. And power, again, power, similar thing. Over here, power is the derivative or the change in energy with respect to time. If you have a constant force, it'll be the force dotted with the velocity. Over here, power is the torque multiplied by the velocity. And it's also, of course, still the change in work with respect to time. I'm going to give this a subscript of power here because we're about to also do momentum. Turns out we have a linear and a rotational momentum. In the linear world, P, notice it's a vector, so it's different from power here, is equal to mass times the velocity. Over here, well, we use L instead, but it's equal to the inertia times the velocity. So for everything that we've done in rotation, we've already previously done something really, really similar in the linear world. And that means that we can do a lot of the same kind of tricks. So for example, if we have constant acceleration, so we've added up all of the net forces and they are constant, and that means we use Newton's second law to find the acceleration. And if we have constant acceleration, we could use any of the constant acceleration equations. So for example, like this one. The position is the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. The velocity is the initial velocity plus the acceleration times time. We could even use the square velocity one. The velocity squared is the initial velocity squared plus 2 times the acceleration times the change in position. But we also have an equivalent over here in rotational world. So if you have constant acceleration, so that is all of the torques on an object are adding up to a constant number, so you can use Newton's second law to find the acceleration, and if that's constant, well then you can use the constant acceleration equation. So the position is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Or you can find the velocity. It's equal to the initial velocity plus the acceleration times time. Or maybe you need to do the square equation. So the square of the velocity is the square of the initial velocity plus 2 times the acceleration times the displacement, or the change in position. And you can also do things like looking at work. So if over here you find all the different works and you sum them up to get the total work, you can set it equal to the change in energy, which is the change in the kinetic energy plus the change in the potential energy. And then over here you can look at the works that are done rotationally, the torque times the change in displacement. And when you add up, well, we actually just don't even have to do anything special. We can just use the kinetic energy, which splits into the change in translational kinetic energy and the change in rotational kinetic energy. So here, we can just say the work, the total work that is, so we've got to sum up all of the works, is equal to the change in the translational kinetic energy plus the change in the rotational kinetic energy plus the change in the potential. And of course that could be gravity and that could be spring. So very similar kind of stuff. So all the math that you need to do for rotational stuff, you pretty much already done for linear stuff, with the exception of these cross products that you need to do to find the torque or find the directions of these position variables. And that's really what you need to think about when you're doing these problems. Think about, does this sound like a problem I've done before in linear world? Then I just got to figure out what the corresponding variables and equations are in a rotational world, but the math will be just the same.